You ever look up at a ceiling or a bridge and just wonder, how does all that actually stay up? It looks so complicated, right? But deep down, it's all about a search for balance. And that whole search starts with one of the most basic building blocks of engineering, the humble beam. So yeah, let's get into it. You know, our story today doesn't kick off in a classroom or some dusty textbook. Nope. It starts with a problem I think pretty much everyone can relate to. That feeling when you're a professional, you're supposed to know your stuff, and you just blank. And this is exactly where we start, right here on Reddit. A user, who's an actual structural engineer, basically admits, hey, I totally forgot how to do the math for these multi-span beams, something they learned way back in school. So they go looking for a tool, any tool, to help them out. And that one question kicks off this whole journey from basic principles all the way to modern software.
Okay, so to really solve our engineer's problem, and to get why the final solution is so cool, we need to learn the language. We gotta speak structures. And it all starts with just a few key ideas that literally hold our world together.
First up, the star of the show, the beam. Really, it's just any piece of material that gets pushed on from the side. The easiest way to think about it is a plank of wood between two sawhorses. You stand in the middle, you're loading it transversely. And what does it do? It bends. That's a beam, plain and simple.
Now those pushes, engineers call them loads, come in different flavors. A point load is exactly what it sounds like, me standing on one single spot on that plank. But a uniformly distributed load, or UDL, that's more like the weight of a heavy snowdrift spread out evenly across a roof beam. Two totally different scenarios, which means, you guessed it, two totally different sets of calculations.
Of course, a beam isn't just floating in space, right? It's held up by supports. The two simplest ones are pins and rollers. A pin support is like a hinge on a door. It holds the beam in place, no up, down, left, or right, but it lets it rotate. A roller support, though, only stops the up and down motion. It lets the beam get a little longer or shorter, say when it gets hot or cold. It's a subtle difference, but trust me, it's a huge deal.
And this brings us to the single most important idea in all of structural engineering. I'm serious. It's called equilibrium. For any structure to not fall down, it has to be perfectly balanced. And that means two things. First, all the forces pushing up have to exactly cancel out all the forces pushing down. And second, all the twisting forces trying to rotate it clockwise, engineers call these moments, have to exactly cancel out all the forces trying to rotate it counterclockwise. That's it. It's simple, it's elegant, and it is absolutely non-negotiable. So, now that we've got the lingo down and we know the golden rule, we can actually do it. We can do what our friend on Reddit was trying to remember. We can take a simple beam and figure out the forces holding it up with just some basic math.
The classic way to do this is a neat little two-step trick. First, you pick one of the supports as your pivot point and you add up all the twisting forces around it. Now, because the grand total has to be 0, this lets you magically solve for the upward push, the reaction force, at the other support. It's brilliant. Then, once you know that one, you just use the second rule. All the ups have to equal all the downs, and you can find the last missing piece of the puzzle.
Let's see this in action. Let's say we have one load pushing down right in the middle of a beam. If we do our math around the left support, that big downward force is trying to spin the beam clockwise. So to stop it, the support on the right has to push up, creating a counterclockwise spin. And for everything to be in perfect balance, that upward push has to be exactly half the downward load. It just makes sense, and the math proves it.
And here's the final beautiful step. We already figured out that the right support, R2, is holding up half the load. And we know the total upward force has to equal the total downward force, P. Well, that means the other support, R1, must also be holding up half the load. The load is shared perfectly, 50-50. It's just a perfectly symmetrical solution.
Okay, doing that calculation every single time is great for understanding the theory. But let's be real. In the professional world, it's all about being efficient. Why derive the formula from scratch when someone's already done the work? This is where engineers turn to the ultimate cheat sheet. They use documents just like this one. It's basically a giant, pre-solved answer key for all kinds of beam problems. Think of it as the official, industry-approved cheat sheet that you are absolutely encouraged to use. Inside, you get the solutions for 32 of the most common situations you're ever going to run into. So instead of working out the formulas every single time, an engineer just flips through, finds the picture that matches their problem, and plugs in the numbers. Done!
And just look at the difference. On the left, that's our snow-covered roof case. On the right, that's our person standing in the middle of a plank. Each one has its own unique diagrams, its own unique formulas, all worked out and ready to go. This is how the vast majority of day-to-day engineering gets done, quickly, reliably, and correctly.
But what about the problem that started this whole thing? That tricky multi-span beam that a Reddit engineer was stuck on. Well, for that, even a book with 32 cases might not be enough. And this is where we come full circle. This is where technology provides the answer.
And here it is, the payoff. After some searching, our engineer finds an online tool, and their reaction says it all. Holy shit, it does everything I was looking for. You can just feel the relief in that comment, right? It's that aha moment when you find the perfect tool for the job.
And it's not just some obscure website. There is an entire world of software out there now designed to solve these exact problems. From simple, free calculators to incredibly powerful professional software like SkySift. The days of being stuck with just a pencil and paper, they're long gone.
So why is the software so important? Well, the answer is a bit of a mouthful. Statically indeterminate. It's a fancy term for a problem where our two simple rules of balance just aren't enough to get the answer. With a beam that has a bunch of supports, you have way more unknown forces than you have rules. It's like trying to solve for x, y, and z when you only have two equations. You can't do it. You need more information, and the math just explodes in complexity. That's when software isn't just nice to have, it's a necessity. And just look at the results. This is what you get from modern software. It's not just a list of numbers. You get these incredibly clear, colorful diagrams that show you exactly what's happening inside that beam along its entire length. It can do something in seconds that would take a person hours, maybe even days, to do by hand. The level of insight you get is just, it's amazing.
So, there you have it. From a forgotten college formula all the way to a powerful piece of software in the cloud, we've seen how the tools to solve this fundamental engineering problem have completely evolved. But the core principle, that beautiful, simple idea of equilibrium, that hasn't changed at all. It kind of makes you wonder, as our tools get even more powerful, what timeless ideas will we still be leaning on in the future?